Okay, so today we're going to be getting into this idea of statistical inference, what exactly that is, and this really important idea of the central limit theorem. Okay, so we've heard this idea of inference or statistical inference before. We know that the study of statistics is kind of broken down into two main areas. Descriptive statistics, we've got all that down. And now we're moving into inferential statistics. Right, so the idea of inferential statistics is we're using a sample to figure something out about the population that it came from. Right? We know about sampling, good sampling techniques, all this kind of stuff. Okay, so we take our sample, we use inference methods to then be able to draw some conclusion, to infer, to generalize about our population. Okay, so we know the idea of what that is. So what are some of these methods that we'll be talking about? Well, the simplest method is point estimation. Okay, that's just using a single statistic that we calculate from our sample to estimate our parameter of interest. Okay, that's as simple as it comes. From there, we might build off of point estimation to construct confidence intervals. We'll see those in the future. We'll also see hypothesis tests. Okay, so not too much on those right now. We're just kind of talking basics here. Right, but eventually what we want to be able to do is for all of these different methods, right, like our sample mean, or x bar, might be a point estimate of our population mean, mu, for all of these different parameters of interest that we might see throughout the rest of the course, we want to be able to apply all of these different methods down this list as we go. So we're going to start at the top of the list. We're going to say, okay, our parameter of interest is mu. Right, so that's where we're going to start because that's the easiest. Okay, so we know what mu means. The lowercase Greek letter mu, that's our population mean. Right, and we know that usually we can't get to the whole population. We can't calculate these parameters. Right, so we have to take a good sample to estimate. So what could we estimate our population mean with? Well, our sample mean. All right, so let's think about, well, would this sample mean be a good estimate? We got to think about, okay, well, what do we mean by good? Right, so we'll talk about that. Right, but let's just think about, we know how to calculate these things. Let's just look at their formulas. So here is our population mean formula. And here's our sample mean formula. Okay, so is this a good estimate of this? Well, I mean, they look pretty similar. Right, our formulas look similar. You would think that just finding the mean of a sample should be pretty close to the mean of the population. All right, so yeah, it's probably a good estimate. What do we really mean by a good estimate? Well, by a good estimate, in our case, in a statistics sense, we mean an estimate that's both accurate and precise. All right, so these are two words that lots of times people use interchangeably, right? But we know that these mean two different things, right? So maybe you've been exposed to this idea before, but here's an example that can kind of demonstrate this idea, right? So if you've ever tried to play golf, you'll know that it's very, very difficult because you have to be very accurate and you have to be very precise, right? I have to hit my ball straight. I have to hit it towards my target, right? And my shot in golf has to be repeatable, has to be predictable, right? A more consistent shot is more precise. So we know that accuracy has more to do with hitting our target or getting the ball in the cup. Precision has to do with how repeatable is this process. Okay, so let's kind of put that in a statistics sense. Right? An accurate estimate then would be something that accurately or correctly, where our statistic correctly estimates the parameter of interest. A precise one would be the more I repeat this process, or the more samples that I take, do these statistics look to be similar, look to be the same? Right? So accuracy, is my statistic close to the actual value of that parameter? Precision, the more I repeat this, how similar are my results? So let's think about this in an example. All right, so if we take a bag of pretzels, right? That bag of pretzels, let's just say it's a good sized bag. It says it's 16 ounces. All right, so we know if you go out and get a bag of pretzels or a bottle of water or a can of whatever you like to drink, right? It's got a number on there, but it may not be exactly 16 ounces or exactly 12 ounces. Right? There's a distribution involved there. The goal of the distributor is usually to get all of their items they're producing to average to whatever it says on the bag. Right? So let's assume that the mean of this population of bags of pretzels, the weights of these bags of pretzels is 16 ounces. And I'll just arbitrarily design a standard deviation of 5 units, right? 5 pounds. Or sorry, not pounds, ounces. Okay, so, and let's also assume that this distribution is normally distributed. We know how to deal with the normal distribution. We'll assume it's normally distributed. So, say this is our population that we're working with. Obviously, we couldn't go out and sample every single bag of pretzels on the planet, weigh them, and see, okay, do these actually average out to 16 ounces? Right, but what we can do is we can go to our closest vending machine, and maybe we have $3. So we take a sample of 3 bags of pretzels. Right, so I take one bag of pretzels, 15.8 ounces, 16.8 ounces, 15.1 ounces. That averages out to 15.9. All right, so 15.9. Pretty good estimate. Now we know mu was 16, x bar 15.9, pretty close. All right, but not perfect. So what's going to happen if we sample again? Well, just because we sample again from the same population, so maybe I go to a different vending machine. 1, 2, 3 bags out of that vending machine. All right, so I get an average here of 15.3 ounces. Go to another vending machine. 3 different bags, 17.43. Another one, 15.83. Right? So we're repeatedly sampling 3 bags of pretzels from, say, 4 different vending machines. I noticed that I got different answers every time. Now our true value is 16. This one's a little bit less, quite a bit less, quite a bit more, and then again just slightly less. What if we think about the average or the mean of these means? Right, we'll take all these, 15.9, 15.3, 17.43, divide by 4 because we took 4 samples, that gives us 16.115. Pretty close to the true mean, but not perfect. This is all to demonstrate this idea of sampling variability. Right? Every time I choose a new sample, the value of that statistic can change. It doesn't mean the value of the actual population parameter is changing. What's changing is the sample that I take and the statistic that I calculate. All right, so when we did this, we only did it 4 times. And these are small samples. Right? We only had $3 in our pocket, so we were only able to get 3 bags of pretzels. So these are small samples, right? But what really could help us is doing this more and more, possibly maybe you're thinking with bigger samples, to really demonstrate this idea of sampling variability and see what happens. And the variability of a sample, the variability of a statistic is reflected, or we can visualize this, in what's called this statistics sampling distribution. Okay, so what's a sampling distribution? Well, if I decide I'm going to take a certain sample size, and I'm going to repeatedly sample samples of this sample size n, all the possible values that this statistic could be and how often it takes them on, is our sampling distribution. Now this is a theoretical idea because we can't take an infinite amount of samples, right? But using some computer tools, computer simulation, we can take a whole bunch of samples and see what we get. All right, so let's see what our sampling distribution looks like and how this ties back to what we were thinking about. All right, so we want an estimate that's both accurate and precise. So when we're visualizing this sampling distribution, we want to think about accuracy as the center of that sampling distribution. All right, we call a statistic where its sampling distribution is centered right at that parameter that we're looking for, we call that an unbiased estimate. Right? Unbiased is a good thing. All right, when we're thinking about the precision of an estimate, the repeatability of an estimate, that is, we can visualize that as the spread of a sampling distribution. We can quantify it as the sampling distribution or the statistics standard error. Okay, so we'll see how we find the standard error in a little bit. Okay, so let's simulate building a hypothetical sampling distribution. And the key here is we're sampling from a normal population. All right, so I'm gonna simulate this hypothetical normal population. Capital N denotes our population size. The mean of mu, standard deviation, sigma. All right, then we're going to take a bunch of samples of sample size N and build these hypothetical sampling distributions. So say our population was made of 100,000 bags of pretzels. Normal population, mean of 16, standard deviation of 5. I'm going to start by taking 1,000 samples of size 5, calculating the mean of each of those samples, and then graphing them, putting them in a histogram. Then that will give us our sampling distribution, and we can see what's going on. Now we're going to repeat this process under different conditions, but here's the questions that I want you to keep in mind as we're going through this simulation. Right, whenever we're trying to describe the distribution of a variable, if we're ever asked to describe a distribution, the first thing that should come to mind is that acronym SOX, shape, outlier, center, spread. Right, so shape should be the first thing that comes to mind. What is the shape of this sampling distribution? Does it seem to depend on something? Now, outliers, since this is a random simulation with hundreds of thousands of items involved, we're not really going to see a lot of outliers, right? So we're not too worried about outliers right now. We are worried about center. Center can check the accuracy. We're worried about spread or the precision. Right? Just like does our shapes seem to depend on something, what does this spread depend on? All right, so here's our hypothetical population. Pretty normal, centered at 16, standard deviation of 5. 100,000 bags of pretzels. So again, here on top is our hypothetical population. On the bottom is a sampling distribution of 1,000 sample means, sample size 5. So we want to think about first the shape. So what does the shape look like? Well, it looks pretty normal. What does the center seem to be? Okay, so we know the center of this population was about 16. I think it's safe to say this center looks to be about 16. So what about the spread? Well, these are both on similar scales. Spread of the population was 5. Sampling distribution here looks to be a little less spread out. Now it's hard to look at it and put a number on it. Okay, we'll put a number on it later, but for now we see it looks to be a little less spread out. Alright, so this is when we had a small sample of size 5. So maybe some of you guys are thinking, well, it's a really small sample. Okay, so let's bump our sample size up and see what happens. So here was our sampling distribution, samples of size 5. Here is our sampling distribution for samples of size 15. Alright. So what do we see happening here as we're adjusting our sample size? Well, we see shape, still looks pretty normal. Center, we've got the actual values highlighted here. The center of this one was 16.17, pretty close to 16. Center here is 15.99, really close to what we're looking for, to 16. Spread, what's happening? Well, this one was less spread out than the population. This sampling distribution looks to be even less spread out. Okay, let's look at the actual numbers. So I calculated the standard deviations. This standard deviation, much less than this one. So again, here's our population, sampling distribution for 1,000 samples of size 5, sampling distribution for 1,000 samples of size 15. Now let's bump our sample size up once more to 30 and see if we see these trends continue. So here's our population, sampling distribution of 5, 15, and 30. So what's happening? Shape-wise, looking about the same across the board. Center, 16, 16, 16, right about 16. So regardless of sample size, things are looking pretty accurate. But a big thing that we see, our standard deviation, or in the case of a sampling distribution, standard error, the spread is going down. Alright, so this is an important idea. Looks like as n is going up, our standard error is going down. In other words, bigger sample sizes are giving us more precise results. Right? More precise is good. So formally answering those questions, pretty normal across the board, pretty accurate across the board, and we see that as n is getting bigger, we're getting more precise. Now remember, this was all from a normal population. All right. So here's kind of summing all of that up in a table. So how do we get these values of spread? Well, I calculated these by just taking all of those different sample means and finding their standard deviation. Right, but we wouldn't want to have to do that every single time. Okay, so we have what's called here our estimated standard error. So how do we estimate our standard error? That's calculated like this. We take our population standard deviation and simply divide by the square root of our sample size. Again, it makes sense. This was the relationship that we saw. As n goes up, our standard error goes down. Makes sense. As n gets bigger and bigger, dividing by a bigger and bigger number, right, this entire quantity is going to get smaller. Alright, so just summing up what we saw when sampling from a normal population, this sampling distribution looked pretty normal across the board. Right, the mean looked to be right around mu, looked to be pretty accurate, and our precision was going down as n went up. That standard error could be approximated by this. Alright, but again, the big point here is that we were sampling from a normal population. So yeah, that makes sense that things would look pretty normal. Right? We know about the normal distribution, we know how to work with it, z-scores, table, all this stuff. Right? So the normal distribution is pretty easy to work with. Right? So we're looking for normality. Right? Sampling from a normal population makes sense that the sampling distribution would be normal. Now we're going to think about What if we sample from a non-normal population? Okay, so there are other non-normal distributions. Here, I decided to use, in this simulation, the exponential distribution. Okay, so first of all, the point here isn't necessarily that it's the exponential distribution. The point here is that it's not a normal distribution. I use the exponential, right, because it looks extremely non-normal. Right? This is what our exponential distribution looks like. Okay, I used here again an exponential distribution of 16. And one interesting thing about the exponential distribution is mean and standard deviation are the same. Okay, so I repeated our previous process, took very similar steps. The difference here is I'm sampling from a non-normal population rather than a normal. I still simulated 100,000 people or things in my population. And I'm going to take 1,000 samples of size 5, 15, and 30, and we're going to see if we see some of the same results, some of the same patterns. All right, so here's my exponential population that I'm sampling from. So I took 1,000 samples of size 5, graphed their sample means, and here's what I got. So shape, we want to keep the same questions in mind. Shape, well, I don't think it looks exactly normal. I think it looks kind of right skewed. Right, we can see some of that original population in the sampling distribution for a small sample size. Let's compare the two. Population, sampling distribution for n equal to 5. Kind of right skewed. Center-wise though, we know this center was 16. This center looks probably about 16. Spread, it's definitely less spread out. Alright, let's bump the sample size up to 15. So 1,000 samples of size 15 graphed their means. This is probably looking a little more normal. Maybe not perfect, but a little more normal. Okay, the mean here, about 16. Standard error getting smaller. All right, bump n up. Now we're looking pretty normal. We're looking pretty normal. Our center's looking to be right around 16, still accurate like we thought, and our spread is getting smaller. So non-normal, specifically exponential population, sampling distribution of size 5, we still see some of that right skewness. Sampling distribution size 15, it's starting to shape up a little bit. Sampling distribution of 30, safe to say it's pretty normal. Right, so we saw some similar patterns. One of the similar patterns that we see is n is going up. What's happening to my standard error here? Yep, looks like it's still going down. All right, but we really see something about the normality. Right? The answers to all of these questions are basically the same. Here is where we see the difference. Sampling distribution starts to look more normal as our sample size gets big. Once we got to 30, we were in pretty good shape. All right. So let's compare these two. So remember, it's sampling from a non-normal population. And what we found was we need big sample sizes in order to see the normality. Things were pretty accurate across the board, and it does look like this estimated standard error value, now I calculated the exact standard errors, the estimated standard error values using sigma over square root of n, these look to be pretty good estimates of each other. Okay? So, comparing these two simulations, normal population, everything looked normal across the board, everything looked accurate across the board, sigma over root n is a good estimate, and as n gets bigger, my standard error goes down. when sampling from a non-normal population, we really had to get a big sample size in order to see that normality emerge. Right? That is what this idea of the Central Limit Theorem says. Okay, the Central Limit Theorem says it doesn't matter what kind of distribution we're sampling from, if our sample size is large enough, we can assume normality of the sampling distribution of the sample mean with parameters mu and standard error sigma over root n. And notice the Central Limit Theorem is a little vague, doesn't give an exact number, it usually says something like it's sufficiently large or large enough. And we just saw in our simulation 30 is usually a pretty generally accepted number. Right? So if we're trying to differentiate, is this a large sample, is this a small sample? 30 is usually our cutoff, our rule of thumb. Alright, so thanks for taking the time to watch this video, and we will pick up with some applications of these ideas in the future.